Oh, you mean A, B, C?
So for 0, 1.
Yeah, we would plug in the endpoints of the interval. It's the exact same reason that we're having to figure out the boundaries of this set. It's like here we're finding out G on the boundaries of this set. It's just the same idea of 1 dimensional. But anyway, we can plug in 1 G. And that gives us -2 plus 5 plus 4, which is 7. Okay. So next. All right. Well, how would we describe boundary B?
It's equal to 1.
From 0 to 1. Good. Oh, I put 0. Okay. So then we figure out what f is when we substitute a 1 in place of x. It'll be a function of y. I'll call it g y. Let's see. If I put a 1 where I see an x everywhere, I'll have 1 plus 4y squared minus 2y plus 4. So we go through the same process. We get a critical value of y equals 1/4. And we do consider that one since it's between 0 and 1. So g of 1/4 is 1/4 minus 1/2 plus 5, which is 19. What next?
Solve for G of y at 0, 1.
So g of 0 is 5, g of 1 is 4 minus 2 plus 5 is 7. So that's boundary B. All right, let's finish boundary C. How would we describe that one?
Y equals 0, x of 0, 1.
Yeah. Okay, so where is our function? There it is. So everywhere we see a y, we put 0 in place, and we get a function of x. So that'll be x squared plus 0 minus 0 plus 4. Its minimum is 0, its maximum is 5. Just a parabola that does this. So, its minimum is at 0, its maximum is at 1. You can go through the work if you want to, but you get g of 0 is 4, g of 1 is 5. There we go. These are the values that we consider for maximum, absolute maximum, and absolute minimum. Here's one, and here's one. So what's the big like
7.
7? Okay.
Four. Oh, wait. Yeah.
that's a problem. Part-time is a problem for me.
We draw towards water, so we're just an exercise in solving systems and equations.
No.
Well, that's right, you suggest that. Okay, we'll just make it.
On the test, if you ask a multiplier question, are you going to be like, oh, here's these two things on the run, but or are you gonna do
Oh,
like you
okay.
did on the practice?
It'll probably, I would rather leave it kind of like I did on the review packet, because then you can solve it using whatever method you want. It turned out that one was a lot easier to solve using the method that we just covered than Lagrange multipliers. So I was kind of limited on. Like this one, for instance, let's find the point, on the plane. Let's say x plus y plus z equals 3. Closest to the sphere, x squared plus y squared plus z squared is 1. Yeah. So what quantity are we trying to either minimize or maximize?
We're trying to maximize the plane.
What's the
You're trying to get it as close as you can, so minimize to the sphere.
minimizing what?
The distance to the sphere.
Distance. So we want to minimize the distance between a point x, y, z and sphere. Might change this, I might reverse it to make it easier in a second. Let me see where this goes. And then sphere x squared plus y squared plus z squared is 1. So we need to write an expression for distance, and we know that distance looks like x minus x naught squared plus y minus y naught squared plus z minus z squared.
So you take your point that you're given on the sphere and no idea.
I think this is too, well, I'm gonna say I think it's too easy. It reduces down to a function of one variable, and that would be a Cowell problem. So let me make it a little right now. Okay. So then this becomes the quantity that we want to minimize. Notice that this quantity is minimized when the stuff under the square root is minimized. I say that because we're going to have to take a gradient of whatever function we want to minimize. I don't really want to take a gradient of the square root function because it will have a bunch of square roots in the gradient. So let's minimize the stuff on the inside.
Those are your constraints, right? Those are your constraints, right?
Here's one constraint. X squared plus y squared plus z squared is 1. 2 times x, 2 times x minus 2, comma, 2 times y minus 2, comma, 2 times z minus 2. And the gradient of g is 2x, 2y, whoops, and 2z. So we generate a system of 4 equations. 2x minus 2 is equal to 2 lambda x. 2y minus 2 is equal to 2 lambda y. 2z minus 2 is equal to 2 lambda z. Together with the constraint. That's the system we need to solve. In order to respond to our problem. In the first equation, I can rearrange terms. 2x minus 2 lambda x is 2. I can divide by 2 and factor in x. instance, that two x minus two is two x, which would mean negative two is the same thing as zero, which is possible. So this is okay to do. We can divide by one minus lambda, it's not the whole story. And you can see that we get the same thing for y and z if you do the same process. You can probably guess which point it is.
I guess it as soon as you got it.
Yeah.
It's square root of 1/3.
Yep. For each x, y, and z. Yeah. You could probably guess because just where the sphere sits in the point sits, extend the line straight through the origin out to the point, and wherever it intersects, the sphere is the point. That we're interested in. And that line is the line in which every coordinate is the same. So since x, y, and z are each equal to these expressions, and we know that x squared plus y squared plus z squared has to be 1, we can sum each of those expressions in place of x, y, and z to get an equation we can solve for. So this means that 3 over 1 minus lambda squared is 1, so that 1 minus lambda squared is 3. That means 1 minus lambda is either plus or minus root 3. And lambda is therefore 1 plus or minus root 3. Common 1 over root 3. Common 1 over root 3. And then we land is equal to 1 minus root 3. Get the negative. So which one corresponds to the max and which one corresponds to the minimum? Now we can tell quickly, I guess, without having to do more math.
Which one's bigger?
Pardon? One of them's got all negative coordinates, one of them's got all positive coordinates, and we're trying to see which one's closer to something with all positive coordinates. So obviously this one has to be the closest, and if this is anything